Decision trees are powerful really when used in ensembles, I mean, combinations of decision trees or regression trees, uh, not as standalone models. Okay, this is the idea of tree ensembles. They combine multiple learned trees to get better accuracy. How to combine it, how to learn such combinations. These are the ensemble techniques or the ensemble types. There are many of these. Generally, they fall in two categories, bagging and boosting. And we'll see how these work. So this is an illustration. This is basically the idea of an ensemble. This is a single decision tree. This is an ensemble of them. We have several decision trees. Each of them makes a prediction, and we make the final prediction by combining the individual predictions. Okay, in terms of how we learn them, bagging would say create different instances of your input, like fragments or samples of your data, learn a model on each of them, and combine. Boosting would say, well, first learn one. Based on what you got and based on the errors that you got and so on, learn the next one. Now you have a better model. Now learn the next one. Each one is improving, boosting the previous, and so in the end, that's usually combine the decisions. Now, this is a typical, chart that you can see in textbooks or in papers showing how the number of trees that you use in your ensemble improves your or helps or changes the accuracy of the model. So this is the error. Smaller is better, and we see here two different models, random forest and the GBM, that's a gradient boosting models. And you see that, and they come here in different configurations. Or the random forest, they use a different M. We'll see what M refers to next. And with GBM, they use the depth of the tree. So these are the hyperparameters. So you see that the more trees you use, generally you get to improve. But in some models, the improvement stops earlier than in others. Okay, so you can get an intuition of how using more trees is helpful. So bagging. We learn several decision trees or regression trees independently. And now, if we just simply learned a decision tree over our data again and again, why would we get a different answer? Well, we need to introduce randomness. We need to allow these trees to reflect different aspects of different cases. So this is what we do. First, we give every learning instance a random sample of our training data, not the full training data, not the same training data, but a random sample of the training data. Each is referred to as a bag, and that's where we're using the terms bagging. Okay. Now, in addition to using a random sample, we when we split a node, we do not look at all of the attributes for a candidate of the splitting condition, but rather first choose m random attributes, like the square root of the number of total number of attributes, and choose from them. This is the m that we saw in the previous slide. Okay, now at inference time, we apply all of the trees to the input, and then we need to make a decision. If it's a classifier, then we can take the majority vote. If it's a regression model, we can use the average or the median. Okay, so you can think of various ways of aggregating different opinions. Okay, boosting. So here is one technique of boosting. This is called reweighting. We learn K decision trees incrementally, and we learn a model that is essentially the sum of the different predictions of the decision trees or regression trees. And you can think of it as, it is weighted. So weighted average or weighted sum of the decision trees. Now, we learn each YL after we learn uh, um, the previous L minus 1. But before we train TL, we reweight the examples. Reweighting the examples means that we are changing the amount that they affect the loss function. Okay, so this the impact of an example is multiplied by the weight. So basically, we make the next model that we learn, next decision tree, more sensitive to some examples than to others. Which ones? Those that we did less well. Okay, did those that we did worse in the previous case. The higher the error of the previous model is, the higher the weight that the example gets. Okay. Now, TL aims to be accurate on the reweighted training set. As far as it's concerned, that's a new problem. Training set with weights, it just tries to be good on that. An example is other boost, where the weight function is something like exponent of minus yi, and the previous model times applied to our example. Okay, and why is it this way? So think of yi as being a minus 1 or 1. So if yi and the previous model are in agreement, then that is a low weight because of the minus here. And if they are disagreeing, then this is a high weight. Okay, so this was reweighting. Let's look at the gradient boosting and think of the following idea first. So we learn again a model, an additive model like previously. And notice that every time we learn a model that adds, and adds to the previous model, ML minus 1, the decisions of the Lth decision tree. So basically what we are doing in gradient boosting is looking not at yi, but actually at the residual, at the difference. What is the difference between what it is that we want to predict yi and what we actually got in the previous model? That's what we're aiming for, and that's what we are training TI to be good on. So we train TL on the residuals rather than the original labels. Okay? And there are several ways of adapting the weights and avoiding these changes to introduce too much diversity or divergence of the model once it gets to some high quality and so on. I'm not getting too much into that. But this is the idea. So we start with one model, okay? And it gets closer to the examples, but there are still residuals, still differences. So we write down these differences, and now we're trying to fit a model to capture these differences. We do what we do, we get a model, but there are still differences. So we write down these differences, okay? The purples here are copied to the other instance, and we fit a model to capture that. In the end, our model is simply the sum of these models. Okay, the combined model. That's the idea. Okay, now where are the gradients getting into the picture? So we denote the previous model, what it says about Ti as Zi. Okay, now we want to learn TL, and once we apply TL, let's call the result Z prime of I. Okay, and we want Z prime of I to be better. We want it to be closer to yi than what Zi is to yi. And then the loss will be smaller with the Z primes rather than the Zs. Okay, now we face the usual dilemma of training. When the model changes and improves significantly, we want to push it forward. We want to be efficient. We wanted to make significant changes to reach to good high quality point. But once we reach good places, okay, and functions of high quality, we want them to improve without too much divergence. We want them to be more careful, more conservative. This is the usual dilemma of learning. And in the past, or in the previous lecture, we used gradient descent, okay, for implementing basically this is such an approach. And gradient descent said, let's look at a different component. These are parameters in our model. Let's see how much they impact locally the loss function. And the step that we are going to take in changing is going to be determined by this impact, which is basically the gradient. Well, here we don't have parameters of a differentiable model, but we apply this idea to the zi's. Basically, for each example, we say, okay, what is the prediction now? Locally, what is the change? What is the gradient of being, better or changing the gradient of this example on the general loss function? If the gradient is high, we aim for a significant change. If the gradient is small, then we'll be conservative. Okay? So, our usual notation, Zi is the current model, Ri is the residual. Okay? And we take the derivative of the loss of with respect to Ti, Yi its label, and Z, okay, which is Zi currently our prediction. And we take the derivative on Z. How much changing Z is going to impact the loss function? Okay, and this is what we train on. Instead of training on the labeled examples, we're training on the gradients, on the R prime i's. Okay, so that's the idea of gradient boosting. And why am I saying that this is how am I relating it basically to the previous idea? Well, the previous idea is essentially this idea in the case where your loss function is least squares. Because if you take the derivative of this function, basically what you will get is that the derivative is the residuals or proportional to the residuals. And so what we did previously was a special case. Okay, so this is gradient boosting. Now, the reason I talked about gradient boosting was to introduce XGBoost, which is really a state-of-the-art system for tabular machine learning, tabular scale, tabular data at scale. Okay, and so it's important to know what this system is about. Basically, it's an advanced implementation and modeling of gradient boosting decision trees. The loss function is pretty straightforward. It's sum of individual losses of the examples. Okay, loss of with respect to yi. This is the label, and what it is that we want to obtain for the next tree ml-1 ti plus t, the tree that we are trying to learn of ti, plus some component that counts the number of leaves. Okay, so this is a regularization that penalizes for the number of leaves, plus a regularization term that penalizes for high weights. Okay, to make the model more careful, basically. That's the regularization. Okay, again, weights are what we learned on the decision trees as the values. This is the numbers that you see in the leaves. Okay, now XGBoost basically comes with a collection of ideas and tricks that make it high quality and scalable. First, you need to take this loss function and translate it into something basically that you use when deciding on the split condition, because that's what that's how the loss is used in decision trees. Basically, in the end, we want to split a node. We want to know what is a good split, and we need a loss function. And we use this loss function. But then, to make it efficient, quickly computable, they use the second Taylor expansion, which uses this first and second derivatives. Okay, so that's in the paper. I'm not really getting into that. They use attribute sampling like in random forest, like we've seen before. They use different ways of having an efficient search of splitting thresholds. Okay, so there are many of these, and again, they aim at scale. So you want to be really efficient. And then how do you use your hardware? Batch processing, parallel computation, efficient management of disk, all of that is in the system. So that's the idea of XGBoost. Additional state-of-the-art models are LightGBM, many ideas similar to XGBoost, and some special ideas like techniques for finding the best leaf to expand, not considering all of the leaves. And another one is CatBoost, which is really specializing on how to use categorical data or how to split nodes in the case of categorical data. And we talked about it in the past, and you want to look at the training data and derive some condition out of that, but you want to avoid leakage of information and they really develop an efficient or a smart technique of doing so effectively. That's all. So that was basically what I wanted to say about machine learning on tabular data and specifically decision trees, ensembles, all the way to state-of-the-art techniques like XGBoost. And next, we're going to look at not just tabular data, but full relational databases and understand how to extract features out of them.